For our first data set, we were given data showing the life expectancies for 40 large countries. Variables included the country, the life expectancy for all individuals, the ratio of the number of people compared to number of televisions, the ratio of the number of people compared to the number of physicians, female life expectancy, and male life expectancy. Using these variables, we're going to find out whether or not life expectancies differ between the sexes. Because we are trying to compare life expectancy between sexes, we will only need to use the variables for male and female life expectancy. All the other variables are considered irrelevant. These two variables are independent of one another and are both simple random samples, so we can use the test statistic to test our null hypothesis, which states that both of these values will have the same mean. For this data, we will use a significance level of 0.05. We will use StatCrunch to test our hypotheses. To do this, we will add all the data onto a new spreadsheet, then go to Stat, tstat, toSample, and with data. For our first sample, we'll select female life expectancy, and for our second, we'll select male life expectancy. To make it easier to see potential differences in the two values, we'll also select Summary Statistic and Dot Plot with Mean Marker. This will show us the mean for both samples, as well as a nice dot plot for all the values of each sample. As we can see from the StatCrunch output, the two means for male and female life expectancies are not the same, but we have to determine whether or not they are significantly different and whether or not this provides sufficient evidence to reject the null hypothesis. To decide this, we must look at the p-value. If the p-value is less than or equal to the significance level, we must reject the null hypothesis. If it is greater than the significance level, we will fail to reject the null hypothesis. Using our significance level of 0.05, we can clearly see that the p-value is less than 0.05. Therefore, we must reject the null hypothesis.
This is the same graph we got from StatCrunch, which clearly shows the dot plot of the two samples with their means highlighted in green. Here we can very easily see how the two samples differ. The mean for female life expectancy is clearly higher than the mean for male life expectancy, and their ranges are different. Based on our data, we can conclude that there is sufficient evidence to reject the null hypothesis that both the mean for male and female life expectancy are the same. There does seem to be a significant difference between the two samples.
For the second data set, we will be analyzing birth weights. We will be looking at the maternal and newborn data for a sample of Seattle, Washington birth weights. The variables presented to us were the gender of the newborn, age of the mother, number of viable pregnancies the mother has experienced, birth weight of the newborn, weight of the mother before pregnancy, weight gain of the mother during the pregnancy, and the length of the pregnancy. Using these variables, we set out to find the best linear model to predict birth weights of newborns. First, we have to identify which of our variables are predictor variables and which is the response variable. In this case, because we are trying to predict the birth weights of a newborn, the birth weight is the response variable. Because all of the other variables pass the common sense test and are relevant to what we are trying to find out, all of the other variables are predictor variables. When picking an equation, it is important to know what to look for. The two main factors are p-value and adjusted r-squared values. We are looking for predictor variables with small p-values, which show us which variables have the most overall significance, and large r-squared values. When looking at equations that have high r-squared values, it's important to remember not to include variables that don't have much effect on their response variable. If two predictor variables have a very high linear correlation coefficient, there is no need to include them both, so the variable with the lower r-squared value can be excluded. In StatCrunch, after we have copied the data over into the new spreadsheet, we go to Stat, then Regression, then Multiple Linear. The y variable is going to be our response variable, birth weight, while the rest of the variables will be added as our x values. The rest will show us a table with all the variables and their p-values, which will help us determine which of these equations we want to use. We can see from looking at the StatCrunch results that gestation is the predictor variable with the lowest p-value, meaning it has the most overall significance of the predictor variables. Because the predictor variable gestation has the lowest p-value, we can conclude that it is the most significant variable in determining birth weight. Because of this, we will use this equation to predict birth weight. Based on our model, gestation is a good predictor of birth weight. However, because the data is taken from Seattle only, it is hard to say whether or not conclusions made can represent the larger population as a whole. This weakens our conclusion slightly, but we can still be reasonably certain enough based on the data provided that our linear model is accurate.